I imagine a world before light could be summoned with the flick of a finger, a world lit only by flame and the patient glow of the sun, where night fell like a curtain and mornings arrived with the slowness of tide. And in that world there lived a curiosity, quiet and persistent, about the invisible forces that moved through everything. Long before anyone understood what it was, electricity existed, waiting in the clouds, hiding in amber rubbed with wool, sleeping in the bodies of strange fish that could stun with a touch. It was always there, woven into the fabric of everything, patient, unmarked, like a language no one had yet learned to read. I think about those early moments when a hand reached toward a doorknob in winter and felt that sudden spark, that tiny rebellion of the invisible, and how that small shock must have seemed like magic, because in a way it was the universe revealing something fundamental, something that had no name, no explanation, just a feeling, a tingle, a mystery wrapped in the ordinary. The ancient Greeks noticed it, too, in their own way. They would rub fossilized tree resin, amber, the color of honey and sunlight, and watch as it pulled small fragments of straw or feather toward itself, as if the amber had woken up, as if it had decided to reach out. They called the amber electron, and that word, soft and golden, would eventually give birth to the name we know today, though they could never have imagined what it would come to mean. In those early centuries, electricity was a whisper, a rumor among philosophers, something to wonder about in the margins of greater questions. It appeared in strange ocean creatures, the torpedo fish, the electric ray that could deliver a shock strong enough to numb a fisherman's arm. And people marveled and feared and tried to understand, but the tools did not yet exist. The framework was not yet built, and so the mystery remained, beautiful and untouchable. I picture those scholars in dim rooms lit by oil lamps, turning pieces of amber over in their hands, running silk across glass rods, watching feathers dance in the air, and writing careful notes about attraction, about invisible influence, about forces that seemed to defy the weight and solidity of the world they knew. They were mapping something they couldn't see, and they were doing it with patience, with the kind of attention that only comes when time moves slowly, when there is no urgency, only wonder. Centuries passed like that, with electricity living quietly in the background of human life, noticed occasionally in moments of static, in the glow of certain stones when struck together in the dark, in the summer storms that split the sky with light and sound. People saw these things, and they wove stories, and they built mythologies around the gods who threw lightning, because what else could explain such power, such sudden, breathtaking force? And then, slowly, so slowly, the questions began to change. The wonder remained, but alongside it grew something else, a kind of systematic curiosity, a desire not just to observe, but to test, to repeat, to isolate, to understand the rules beneath the spectacle. This shift took generations. It required new instruments, new ways of thinking, new patience. But it was beginning, like the first light of dawn, barely visible, but unmistakable to those who were watching. I think about how different the world must have felt in those in-between centuries, when the old explanations were fading, but the new ones hadn't yet arrived, when electricity was still a mystery, still a wonder, but beginning, just beginning to reveal its nature, to show that it could be coaxed, directed, studied, that it followed patterns, that it was not chaos, but order waiting to be discovered. The path from those early observations to the world we know today is long and winding and filled with moments of sudden insight and long stretches of patient, methodical work. It's a path that moves through centuries, across continents, through the minds of countless individuals who each added a piece, a fragment, a new way of seeing, until the invisible became visible, until the mystery became a tool, until the spark became the foundation of everything we touch. And so I begin there, in that quiet time before understanding, when electricity was still wild, still untamed, still waiting, because that's where every journey into knowledge begins, in the not knowing, in the space between the question and the answer, where everything is still possible, and the night is long, and the amber glows softly in the lamplight, pulling feathers toward itself, for reasons no one can yet name. The first person to truly study this invisible force with careful, deliberate attention was a man named William Gilbert, a physician to Queen Elizabeth I, living in England at the turn of the 17th century. He was not the first to notice the strange behavior of rubbed amber, but he was among the first to approach it with the mind of a scientist, with the patience of someone willing to test and test again, and record what he found. Gilbert spent years experimenting. He rubbed different materials together, amber and glass and sulfur, and he watched what they attracted. He discovered that many substances, not just amber, could be made to pull lightweight objects toward them after being rubbed, and he called these materials electrics, from that ancient Greek word, electron. He was giving a name to a category, creating a vocabulary where none had existed, and in doing so, he was building the foundation for everything that would follow. In 1600, Gilbert published his findings in a book called De Magnete, which means on the magnet, and though the book was primarily about magnetism, it contained those crucial observations about electricity, about this other invisible force that seemed related to magnetism, but different, distinct, operating by its own rules. The book spread slowly through Europe, copied by hand, discussed in universities, passed between curious minds who were beginning to see the world as something that could be understood, not just accepted. Time moved differently then. A discovery might take decades to travel from one country to another. An idea might sit dormant for a generation before someone picked it up again. There was no rush, no race, just a slow accumulation of knowledge, like sediment settling at the bottom of a river, building up layer by patient layer. In 1660, a German inventor named Otto von Guericke created something remarkable. He built a machine, a sulfur globe that could be rotated and rubbed by hand. And when it spun, it generated static electricity, not just a little spark, but enough to create a visible glow in the darkness, enough to make a sound, a crackling like tiny thunder. This was the first electrical generator, crude and simple, but it was the beginning of something, the first time humans had created a sustained source of this mysterious force, had made it appear on demand. Von Guericke showed his machine to audiences, and they were amazed. They watched the globe glow in the dim light of evening, heard the crackle and snap, felt the tingle when they touched it, and they didn't fully understand what they were witnessing. but they knew it was important. They could feel it, the way you can feel the air change before a storm, that sense of something significant, something that would matter. Others began building similar machines, improving on the design, using glass instead of a sulfur, adding mechanisms to store the charge. Each improvement was small, incremental, but together they were building a toolkit, a set of instruments that would allow electricity to be studied, manipulated, understood. The invisible was becoming, if not visible, then at least tangible, something that could be worked with, shaped, directed. In the 1700s, the pace began to quicken just slightly. A French chemist named Charles-François de Cisternay Dufay discovered that there were two types of electricity. He rubbed different materials and found that sometimes they attracted each other, and sometimes they repelled. He called these two types vitreous and resinous, what we would later come to know as positive and negative charges. But he didn't know that yet. He just knew there were two, and that they behaved in opposite ways, like two sides of the same coin, like shadow and light. Around the same time, in the Netherlands, a professor named Peter van Musschenbroek was working with a glass jar, a simple container, partly filled with water, with a metal wire running through a cork in the top. He connected the wire to an electrical generator, and the jar began to store the charge, to hold it, like a vessel holding water. And when he touched the jar while it was charged, he received a shock so powerful it knocked him backward, so intense he later wrote that he wouldn't repeat the experiment for the Kingdom of France. This device became known as the Leyden jar, named after the city where it was developed, and it changed everything. Suddenly, electricity could be stored, accumulated, released all at once. It meant that experiments didn't have to happen in real time with a generator running. It meant the charge could be transported, shared, studied at leisure. The Leyden jar became the battery of its age, the first capacitor, and every laboratory that wanted to study electricity had to have one. I imagine those early experimenters working in their studies and workshops, surrounded by glass jars and spinning globes and metal chains, trying to understand the rules, the patterns. They would charge a jar, then touch it to different materials, seeing what conducted and what didn't. They would link jars together, creating larger and larger stores of electricity, and then discharge them all at once, creating sparks that jumped across gaps, that lit up the darkness, that made sounds like miniature lightning. And speaking of lightning, that was the great question of the age. The mystery that captured everyone's imagination. Was lightning the same as the electricity they were creating in their laboratories, or was it something else entirely? Something divine, something beyond human understanding? The question hung in the air, unanswered, waiting for someone brave enough, or perhaps foolish enough, to test it. That person was Benjamin Franklin, a printer and writer and inventor living in Philadelphia, in the American colonies. He had read about the electrical experiments happening in Europe, and he had begun conducting his own. He noticed similarities between lightning and laboratory electricity, the way both created light, made sound, followed similar paths, struck high points, and he began to suspect they were the same thing, the same force, operating at vastly different scales. In 1752, Franklin performed his famous experiment. Though the details have been embellished over the years, he flew a kite in a thunderstorm. a kite with a metal wire attached to it, and at the end of the string, near where he stood, he attached a metal key. The idea was simple but dangerous. If lightning was electrical, it would travel down the wire, down the wet string, and he would be able to detect it at the key. The experiment worked. He saw sparks jumping from the key, felt the charge, and in that moment he proved what he had suspected. Lightning was electricity, the same force that made amber attract feathers, the same force that charged Leyden jars, but amplified, intensified, unleashed by nature with a power that dwarfed anything humans could create. The sky and the laboratory were connected. The divine and the mundane were one. Franklin's discovery was profound. It meant that this invisible force was everywhere, in everything, not just a curiosity, not just a parlor trick, but a fundamental aspect of the natural world, as basic as gravity, as essential as air. And if it was everywhere, if it followed rules, then perhaps it could be harnessed, used, put to work. Franklin invented the lightning rod, a simple metal pole placed at the highest point of a building, connected by wire to the ground. The idea was that lightning would strike the rod instead of the building, and the electricity would flow harmlessly into the earth. It was the first practical application of electrical knowledge, the first time humanity had used understanding of this force to protect itself, to work with nature rather than simply fear it. The lightning rods spread, slowly at first, then more rapidly, appearing on churches and government buildings, on homes and barns. Some people objected. They thought it was wrong to interfere with divine judgment, that lightning was God's will and shouldn't be redirected. But the rods worked, buildings stopped burning, lives were saved, and gradually resistance faded, replaced by acceptance, by the recognition that understanding nature didn't diminish its wonder. It just made it less deadly. Throughout the 1700s, more discoveries followed. More pieces of the puzzle fell into place. Scientists learned to distinguish between conductors and insulators, between materials that allowed electricity to flow freely and those that blocked it. They discovered that metals were excellent conductors, that glass and rubber and silk were insulators, and they used this knowledge to build better instruments, more precise experiments. In Italy, a professor named Luigi Galvani was dissecting frogs, as one did in the 18th century, and he noticed something strange. When he touched the frog's leg with two different metals at the same time, the leg would twitch, would move as if alive. Even though the frog was long dead, he believed he had discovered animal electricity, a special life force that existed in living tissue. But another Italian scientist, Alessandro Volta, disagreed. He believed the electricity was coming from the interaction of the two different metals, not from the frog. The frog was just responding, just conducting, but it wasn't the source. To prove his theory, Volta built a device, a stack of alternating zinc and copper discs, separated by cloth soaked in salt water. And when he touched wires to the top and bottom of the stack, he got a steady flow of electricity, continuous, reliable, not just a single shock like a Leyden jar, but a sustained current. This was the first true battery, invented in 1800, and it was revolutionary. For the first time, electricity could flow continuously, could be directed through wires, could power experiments for minutes or hours instead of just moments. Volta's pile, as it came to be known, opened doors that had been closed. It allowed scientists to study electrical current, to measure it, to understand how it moved and what it could do. The world was changing, imperceptibly at first, but changing nonetheless. These discoveries were happening in scattered locations in different countries, shared through letters and journals and occasional meetings, but they were building on each other, creating a foundation, a structure of understanding that would soon support something much larger, something that would transform not just science, but civilization itself. And still, in 1800, in the homes of ordinary people, none of this mattered yet. Life was still lit by candles and oil lamps. Power still came from muscle and water and wind. The discoveries were fascinating to scholars, but they hadn't yet touched the daily rhythm of human existence. They were seeds planted in fertile ground, waiting for the right conditions, the right minds, the right moment to burst into bloom. That moment came in the 1820s, when a Danish physicist named Hans Christian Ørsted was demonstrating electrical circuits to his students. He had a wire connected to a battery, and current was flowing through it, and nearby, purely by chance, there was a compass sitting on the table, and as the current flowed, the compass needle moved, twisted away from north, responding to something invisible emanating from the wire. Ørsted saw it and understood immediately what it meant. Electricity and magnetism were connected. They weren't just similar forces. They were intimately related, intertwined, two aspects of something deeper. This discovery rippled outward, reaching other scientists who seized upon it, who began exploring this relationship, probing its boundaries, testing its limits. In England, a man named Michael Faraday, who had started his life as a bookbinder's apprentice, who had taught himself science by reading the books he was supposed to be binding, took Ørsted's discovery and pushed it further. If electricity could create magnetism, could magnetism create electricity? Could the relationship flow both ways? Faraday was not a mathematician. He didn't work in equations. He worked with his hands, building apparatus, wrapping coils of wire around iron rings, moving magnets near conductors, feeling his way toward understanding, and in 1831 he discovered electromagnetic induction. He found that when he moved a magnet through a coil of wire, electricity flowed in the wire, not from a battery, not from a chemical reaction, but from motion, from the simple act of moving one thing near another. This was the principle that would power the world, the idea that motion could create electricity, that a turning wheel or a flowing river could be converted into this invisible current. It meant that electricity didn't have to come from batteries that would eventually run down. It could be generated continuously, endlessly, as long as something was moving. Faraday built the first primitive generator, a copper disc that rotated between the poles of a magnet, and as it spun, current flowed. It wasn't much, just a trickle, but it was proof. It was a door opening, and through that door lay everything, every light bulb, every motor, every humming wire that would eventually crisscross the planet. I imagine Faraday in his laboratory at the Royal Institution in London, surrounded by coils and magnets and jars of chemicals, his notebook open, recording every observation, every variation. He wasn't trying to build something practical, not yet. He was trying to understand, to see the invisible patterns, to trace the lines of force that he believed filled all of space, connecting everything to everything else. While Faraday was experimenting, other minds were working on the mathematical foundation. In Scotland, James Clerk Maxwell was developing equations that would describe electricity and magnetism as unified phenomena, waves propagating through space. He showed that light itself was an electromagnetic wave, that the visible spectrum was just a small slice of a much larger reality, that radio waves and X-rays and all the invisible radiation that fills the universe were all the same thing, electricity and magnetism dancing together, creating ripples in the fabric of space. But equations and theories, however beautiful, don't light homes or power machines. For that, electricity needed to become practical, usable, cheap enough and safe enough to leave the laboratory and enter the world. The first practical applications were in telegraphy. Samuel Morse in America and Charles Wheatstone in England developed systems that could send messages over wires, dots and dashes, pulses of electricity representing letters, and suddenly, for the first time in human history, information could travel faster than a horse could run, faster than a ship could sail. Messages that would have taken weeks to deliver now arrived in minutes. Telegraph wires began stretching across continents, under oceans, connecting cities and countries. The world was shrinking, time was compressing, and electricity was the force making it possible. But telegraphy was just the beginning, just a hint of what was coming. In the 1870s and 80s, the race to create electric light began in earnest. Dozens of inventors worked on the problem, trying to find a material that would glow when electricity passed through it, that would glow brightly, steadily, without burning up too quickly. The challenge was finding the right filament, the right material to put inside a glass bulb to heat until it glowed like a tiny sun. Thomas Edison in America, Joseph Swan in England. Both arrived at similar solutions around the same time. A carbon filament sealed in a glass bulb with the air removed could glow for hours, for days, providing steady, clean light without flame, without smoke, without the constant need for fuel. Edison built his first successful bulb in 1879, and he knew immediately that this was more than an invention. It was the beginning of a transformation. But a light bulb by itself was useless. It needed electricity to flow to it, continuously, reliably, and that meant building an entire system, generators to create the power, wires to carry it, switches to control it, meters to measure it. Edison understood this. He wasn't just inventing a product, he was inventing an infrastructure, a network, a new way of organizing energy and space. In 1882, Edison opened the first commercial power station on Pearl Street in New York City. It had 6 generators powered by coal-fired steam engines, and they fed electricity through underground cables to 59 customers in the surrounding blocks. The system used direct current, electricity flowing in one direction, like water through a pipe, and it worked. Lights came on in offices and homes, steady and bright, and people gathered to watch, to marvel at this new thing that seemed like magic, but was really just understanding, applied with patience and precision. The early power stations were small, serving just a few blocks, because direct current couldn't travel far without losing strength. The voltage would drop over distance, and so every neighborhood needed its own generator, its own coal pile, its own engine house with men shoveling fuel day and night. It was practical, but limited. constrained by the physics of how electricity moved through wires. In Europe, another inventor was thinking about this problem differently. Nikola Tesla, a Serbian engineer working in France and then America, believed that alternating current electricity that reversed direction many times per second could solve the distance problem. Alternating current could be stepped up to very high voltages for transmission, then stepped down again for use. And high voltage meant less loss over long distances, meant one generator could serve an entire city or more. Tesla designed motors and generators for alternating current, elegant machines that took advantage of the reversing flow, and he tried to convince Edison to switch systems. But Edison had invested too much in direct current, had built too much infrastructure, had made too many promises. The two men and the companies behind them went to war, not with weapons, but with demonstrations and publicity, each trying to prove their system was superior, safer, more practical. The battle was fierce, public, sometimes ugly. Edison held demonstrations where he electrocuted animals with alternating current, trying to show it was dangerous. Tesla and his backer, George Westinghouse, built power stations and long-distance transmission lines, proving the system could work, could do things direct current never could. The struggle lasted years, filled newspapers, captured the public imagination. In the end, physics won. Alternating current could simply do more, could travel farther, could power larger areas from fewer stations. In 1893, Westinghouse won the contract to light the world's Columbian Exposition in Chicago, and when those lights came on, hundreds of thousands of them illuminating buildings and fountains and pathways, turning night into day across the fairgrounds, the world saw what electricity could be, what it could do, and the future was decided. That same year, work began on harnessing Niagara Falls, building generators that would convert the endless flow of water into electricity, and sending that power to Buffalo, 20 miles away. It was a project that seemed impossible, audacious, but it worked. The generator spun, the power flowed, and for the first time, a major city was lit by electricity generated far away, by the raw force of nature captured and transformed. I think about what it must have been like to live through that transition, to remember when night was dark, truly dark, when the only light after sunset came from flames, and then to see streets lit by electricity, steady and bright and always there, to flip a switch and have light appear, instant, reliable, like sunrise on demand. The changes came faster after that. Electric streetcars replaced horse-drawn ones, cleaner, faster, not limited by how tired the animals were. Electric elevators made tall buildings practical, allowing cities to grow upward instead of just outward. Electric motors began appearing in factories, each machine with its own motor, instead of all being connected to a single steam engine by belts and pulleys. Workers could arrange equipment for efficiency instead of just proximity to the power source. Homes began to change too, slowly at first. Electric irons, electric fans, electric stoves and heaters. Each new device was expensive, a luxury, but as more people bought them, as production scaled up, prices fell, and what was once available only to the wealthy became ordinary, expected. The electric grid spread, reaching smaller towns, rural areas, climbing up poles along country roads, bringing light and power to farmhouses that had never known anything but lanterns. By the early 1900s, electricity was becoming fundamental, not just a novelty, but a necessity. Cities were rewiring themselves. New buildings were designed around electrical systems from the start. Old ones were retrofitted, walls opened, wires threaded through. Electrician became a profession, a skilled trade, and linemen climbed poles to string wire after wire, connecting homes and factories and offices into a growing web of power. The light bulb evolved, became more efficient. Tungsten filaments replaced carbon, lasting longer, burning brighter. Glass manufacturing improved, making bulbs cheaper, more uniform. And with better bulbs came new uses: street lights, car headlights, flashlights, surgical lamps. Every problem that had once been solved with flame was being reconsidered, reimagined, improved. And electricity was doing more than just making light. It was enabling communication on scales never before possible. The telephone, invented by Alexander Graham Bell in 1876, used electricity to carry voices across wires. At first, just across a room, then across a city, then across continents. Switchboards staffed by operators connected call after call, voices traveling as electrical signals, converted to sound at the other end. People could speak to each other across impossible distances, could share news, conduct business, maintain relationships that distance would once have severed. Radio came next. Guglielmo Marconi and others learning to send signals through the air itself, no wires needed, just electromagnetic waves propagating through space, exactly as Maxwell had predicted. By the 1920s, radio stations were broadcasting, voices and music reaching into homes, creating shared experiences, connecting scattered communities into something larger. The invisible spectrum was becoming a highway, carrying information, entertainment, news, all powered by electricity, all moving at the speed of light. The 1920s and 30s brought electricity fully into the mainstream of life. No longer a marvel to demonstrate, but a utility to depend on. So power plants grew larger, more efficient, burning coal or oil, or harnessing falling water, spinning massive generators day and night, feeding an ever-hungry grid that stretched farther each year, reaching into valleys and across plains, climbing mountains, crossing deserts. Rural electrification became a mission, a project. In America, the Tennessee Valley Authority built dams and power stations, strung thousands of miles of wire, bringing electricity to regions that had been left behind in the first wave of development. Farms that had relied on muscle and sunlight suddenly had power tools, electric pumps for wells, lights in barns, refrigerators to keep food fresh. The transformation was profound, reshaping not just work but culture, possibility, the sense of what life could be. Electric refrigeration changed how people ate. Before, food preservation meant smoking, salting, canning, or eating quickly before spoilage. Ice boxes required ice, delivered by men who cut it from frozen lakes in winter and stored it in sawdust. But electric refrigerators kept food cold continuously, reliably, expanding what could be stored, what could be cooked, what could be planned. Kitchens became different places, equipped with electric stoves and mixers and eventually dishwashers, each appliance reducing the hours of labor that had once defined domestic life. Air conditioning arrived, first in theaters and department stores, then in office buildings, gradually in homes. It used electricity to move heat, to make indoor spaces cool even when outside the summer blazed. This changed where people could live comfortably, changed architecture, changed cities in the American South and Southwest. Places that had been seasonal or sleepy became year-round, vibrant, powered by the ability to control climate, to make anywhere temperate. World War II accelerated everything. The demands of war required massive industrial production, aircraft factories, shipyards, munitions plants, all running around the clock, all consuming electricity at rates that would have been unimaginable a generation earlier. New power stations were built in months instead of years. Aluminum production, essential for aircraft, required enormous amounts of electricity, and dams were built specifically to supply it. The war proved that electricity could be scaled, could support civilization at its most intense, its most demanding. And during the war, a new use for electricity emerged, one that would eventually rival even lighting in its impact. The first electronic computers were built, massive machines filling entire rooms, using thousands of vacuum tubes that glowed with heat and light, consuming kilowatts of power to perform calculations. These early computers were built to crack codes, to calculate artillery trajectories, to solve problems too complex for human minds working alone. After the war, the computers didn't disappear. They evolved, improved. Vacuum tubes gave way to transistors, solid-state devices that did the same work with less power, less heat, less space. Transistors gave way to integrated circuits, chips containing thousands, then millions, then billions of tiny switches, all controlling the flow of electricity at scales so small they approach the atomic. And through all these changes, electricity remained fundamental, the force that moved through the circuits, that represented information, that made computation possible. The second half of the 20th century saw electricity become so thoroughly woven into daily life that its presence became invisible, taken for granted. People stopped thinking about it except when it failed, when a storm knocked down lines or a transformer blew, and suddenly the silence was deafening. The hum that had become the background of civilization stopped, and in that silence, people remembered how dependent they had become, how much they relied on this invisible flow of energy. Cities at night became landscapes of light, streets illuminated, buildings glowing, signs flashing. From above, from an airplane or a satellite, the lights traced the shapes of human settlement, bright clusters connected by luminous threads. The nighttime earth became a mirror of the daytime, not dark anymore, but alive with artificial suns, billions of light bulbs and fluorescent tubes and later LEDs, all drawing current from the grid, all pushing back the darkness that had defined night since the beginning of time. Nuclear power emerged, a new way to generate electricity, splitting atoms instead of burning coal, using the heat from controlled fission to boil water, to spin turbines, to turn generators. The first commercial nuclear power plant opened in 1957 in Pennsylvania, and others followed. Each one could produce enormous amounts of power without smoke, without the mountains of coal or rivers of oil that conventional plants required. Though the technology brought its own challenges, its own fears and careful regulations, it proved that electricity could come from the very structure of matter itself, from Einstein's famous equation made practical Solar panels appeared, devices that converted sunlight directly into electricity, using the photoelectric effect that Einstein had explained decades earlier. At first they were expensive, inefficient, used mainly in space where the advantages outweighed the cost. But gradually, year by year, they improved, became cheaper, more practical. People began putting them on roofs, in fields, in deserts, harvesting light, turning photons into current, closing a circle that stretched back to the sun, the ultimate source of nearly all energy on Earth. Wind turbines grew, evolved from small farm windmills into massive structures with blades longer than airplanes, standing in fields and offshore, turning steadily in the breeze. Their generators spun in the wind, producing electricity that fed into the grid alongside power from coal and gas and nuclear. The mix was changing, diversifying, moving towards sources that could be sustained indefinitely. That didn't depend on ancient carbon pulled from the ground. Through all this growth, all this evolution, the fundamental nature of electricity remained what Faraday and Maxwell had discovered, what Edison and Tesla had harnessed: electrons flowing through conductors, moving in response to voltage, creating magnetic fields, doing work. The physics hadn't changed, but humanity's ability to use them, to channel them, to build civilization around them, had grown beyond anything those early experimenters could have imagined. I think about the scale of it now. The global grid, not truly connected everywhere, but vast nonetheless. Generating stations by the thousands, transmission lines strung across continents, substations stepping voltage up and down, transformers on poles, wires running to every building, circuits behind every wall, electricity flowing constantly, invisibly, supporting everything, every computer, every light, every motor, every heater and cooler and communicator, all drawing from the same fundamental force that made amber attract feathers in ancient Greece. The internet arrived, computers connecting to computers, first in universities and government, then spreading, becoming commercial, becoming personal. Each connection required electricity, servers in climate-controlled rooms, routers directing traffic, fiber optic cables carrying light instead of electrons, but still requiring power to generate and detect that light. The digital world, the virtual spaces where so much of modern life happens, all of it runs on electricity. All of it would vanish instantly and completely. If the power stopped, mobile phones emerged, small computers that fit in a pocket, connected wirelessly to networks, to the internet, to each other. Each one contains a battery, a descendant of Volta's pile, storing electricity chemically and releasing it on demand. They charge from the grid, drawing power overnight or throughout the day, converting alternating current to direct, stepping voltage down, filling the battery so the device can run for hours, for days, before needing to connect again. Electric vehicles began to appear, first as experiments, then as products. Cars powered by batteries instead of gasoline, motors instead of engines. They represented a return to the early days of automobiles, when electric cars briefly competed with internal combustion, before the limitations of battery technology made them impractical. But a century of improvement in batteries, in motors, in power electronics, made them viable again, practical, increasingly common. The same grid that lit homes could now power transportation, could replace the burning of fuel with the flow of electrons. And still, underneath all the applications, all the devices and systems and networks, the basic reality remained simple. Electricity is the movement of charge, the flow of electrons through conductors, responding to voltage, creating effects. It can be generated by motion, by chemical reactions, by light, by heat. It can be stored, transmitted, transformed, used to create light or motion or heat or information. It follows laws that were discovered and described in the 19th century, laws that still hold, that still explain everything from the smallest circuit to the largest power grid. The story of electricity is the story of understanding, of taking something mysterious and invisible and learning its rules, its patterns, its possibilities. It's the story of patient observation, careful experiment, mathematical description, and then, crucially, practical application. The gap between knowing how something works and building useful things with that knowledge is vast, and crossing it required not just scientists, but engineers, entrepreneurs, electricians, linemen, regulators, investors, millions of people, each contributing a piece, each adding to what came before. As I trace this history from amber and wool to the electric world we inhabit now, I'm struck by the continuity, the way each discovery built on previous ones, the way understanding deepened gradually, layer upon layer. No single person invented electricity or discovered all its properties. It was revealed slowly through the work of many minds across many generations, each seeing a bit further, each adding to the collective knowledge, until the invisible became visible, until the mysterious became mundane, until the force that once seemed magical became the foundation of everything. And perhaps that's the most remarkable thing, not that electricity powers our world, but that we learn to understand it at all, that we mapped the invisible, that we found the patterns in phenomena that our ancestors could only wonder at. That journey from mystery to mastery took centuries, required brilliance and persistence and countless failures, but it happened step by patient step, spark by tiny spark, until the darkness retreated and the modern world emerged, humming with current, alive with light. The deeper I move into this story, the more I realize that electricity is not just about power or light or convenience. It's about revealing the invisible architecture of reality, about discovering that the world operates according to rules we can learn, patterns we can predict, forces we can work with rather than simply endure. Before electricity was understood, the universe seemed more arbitrary, more capricious. Lightning struck without warning or reason. Sparks appeared mysteriously when wool touched amber. The northern lights danced in the sky with no explanation. These phenomena existed in the realm of wonder, of mythology, of divine intervention. But as people began to study them, to test and measure and theorize, the wonder didn't disappear. It transformed into something else, a different kind of awe, the recognition that nature follows laws, elegant and consistent, waiting to be discovered. There's something profound about the fact that the same force powers a thunderstorm and a light bulb, that the electricity in your nervous system, the signals moving from brain to muscle, from sense to thought, is fundamentally the same as the electricity in the wires behind your walls. It's all electrons, all charge and motion, all following the same principles that Maxwell described in his equations. The universe is unified in ways that aren't immediately obvious, and electricity was one of the first windows into that unity. I think about how electricity changed our relationship with time. Before artificial light, human activity followed the sun. Work happened during daylight. Evening was for rest or simple tasks by firelight. The rhythm of life was tied to the rotation of the earth in ways it had been since consciousness began. But electric light broke that connection, made night into day, allowed work and activity and thought to continue regardless of the sun's position. Factories could run 3 shifts. Cities could stay awake. The circadian rhythms that had governed humanity for millennia suddenly faced competition from human-made light, constant and controllable. This wasn't entirely good, wasn't entirely progress without cost. We've learned that constant light disrupts sleep, confuses the biological systems that expect darkness, that need it, but it happened, and it can't be undone. The electric world doesn't turn off, doesn't sleep. It hums through the night, powering streetlights and hospitals and data centers, maintaining the infrastructure of connection and commerce that never pauses. And electricity enabled a kind of precision that wasn't possible before. When power came from water wheels or windmills or steam engines, it was variable, dependent on conditions, but electricity can be controlled with exquisite accuracy, voltage regulated to within millivolts, current adjusted in microseconds. This precision made possible everything from medical equipment to semiconductor manufacturing to the timing systems that keep the internet synchronized. Without the fine control that electricity allows, the modern world's complexity couldn't exist, couldn't function. There's also something worth considering about how invisible it all is. Most people use electricity constantly without thinking about where it comes from, how it's generated, how it reaches them. They flip switches, plug in devices, expect light and power and connection, and receive them, the infrastructure that makes this possible. The generating stations and transmission lines and transformers and substations, most of it is out of sight, taken for granted, noticed only when it fails. This invisibility is both a triumph and a vulnerability. A triumph because it means the system works so well, so reliably, that it fades into the background, becomes as expected as air or gravity. But a vulnerability because invisible systems are fragile systems. People don't protect or maintain or understand things they can't see, and the grid, for all its redundancy and robustness, is still susceptible to storms, to equipment failure, to the simple wear of time. We've built a civilization that depends entirely on something most people don't understand, can't see, can only trust, will keep flowing. Yet perhaps that trust is justified. The electrical grid is one of humanity's greatest collective achievements, a system that requires cooperation across jurisdictions and companies and countries, that requires constant maintenance and upgrading and balancing, that works because thousands of people, engineers and technicians and planners, make it work every day, every hour, adjusting loads and routing power and fixing problems before most people know they exist. And the story continues, still unfolding. Solar panels become cheaper, more efficient. Wind turbines grow larger, more capable. Battery technology improves, able to store more energy, discharge it more reliably. The grid is transforming again, becoming more distributed, less dependent on massive centralized plants, more resilient, more sustainable. The next chapter is being written now by engineers and scientists working on problems their predecessors couldn't have imagined, using tools that wouldn't exist without electricity to solve challenges about electricity itself. There's a poetry to it, a circularity. We use electricity to understand electricity, to improve the systems that generate and distribute it, to create the computers that model better batteries, better solar cells, better ways to manage the complexity of a grid that connects millions of sources and consumers. The tool has become both the means and the object, both the question and the answer. As I consider the long arc of this story, from Gilbert's experiments with amber to the global grid that powers billions of devices, I'm aware of how much had to align, how many minds had to be curious in the right ways, how many experiments had to succeed or fail in useful ways, how many practical problems had to be solved. The path from discovery to application is never straight, never simple. It requires not just understanding but engineering, not just knowledge but infrastructure, not just invention but adoption, and yet it happened relatively quickly in the scope of human history. A person born in 1850 might have lived by candlelight as a child and died in a home with electric lights and a telephone and a radio, might have witnessed the entire transformation from mystery to utility, from wonder to mundane necessity. How strange that must have been, to watch the world change so fundamentally, to experience the before and after of a revolution that touched everything. Now the change continues, but differently. We're not discovering electricity anymore. We're refining our use of it, making it cleaner, more efficient, more ubiquitous. We're putting it in new places, new devices, finding new applications for the same fundamental force. The physics is settled, the mystery is solved, but the possibilities keep expanding, keep surprising us with what else can be done, what else can be built, what else can be imagined and then made real. And in all of this, in the complexity and the infrastructure and the applications, the basic wonder remains if we choose to see it. That moving a magnet near a wire creates current, that light and radio waves are the same phenomenon, that the spark you feel touching a doorknob is the same force that lights cities and powers computers and connects the world. These facts, established and certain, are still remarkable, still worthy of attention, still beautiful in their simplicity and their implications. The story of electricity is ultimately a story about human capacity, about our ability to observe, to question, to test, to understand, to build, to transform knowledge into power, into light, into connection. It's a story that isn't finished, that continues in laboratories and power plants and homes, in every device that draws current, in every wire carrying charge from place to place, in every mind still curious about how things work and how they might work better. And so I find myself here at the end of this long contemplation, having traced the arc from ancient amber to the electric present, from mystery to mastery, from darkness to perpetual light. The story could continue, could branch into 1,000 tributaries, each interesting, each worthy of exploration. But perhaps this is enough. Perhaps the outline is clear. Electricity is everywhere now, in everything. It's in the device displaying these words, in the networks that transmitted them, in the lights illuminating the room, in the refrigerator humming in the kitchen, in the car waiting to be charged, in the phone in your pocket, in the infrastructure underlying civilization, invisible but essential, taken for granted, but remarkable. I think about those early experimenters, Franklin with his kite, Faraday with his coils, Maxwell with his equations. They were trying to understand something invisible, something that couldn't be seen or held, only felt, only inferred from its effects. And they succeeded. They mapped the territory. They found the rules. They gave us the knowledge that others would build upon, would transform into the electric world we inhabit. And that world keeps changing, keeps evolving. The next generation will tell their own stories about electricity, about new ways to generate it, store it, use it. They'll solve problems we haven't fully recognized yet. They'll make improvements we can only imagine. But they'll build on the same foundation, the same understanding, the same fundamental physics that was discovered in laboratories centuries ago by people who were simply curious, who wanted to know why amber attracted feathers, why lightning struck, what this invisible force might be. The circle completes itself in a way. We began with wonder, with mystery, with things unexplained, and now, having explained so much, having harnessed and controlled and built with electricity, we can return to wonder, can choose to see the remarkable in the everyday, can appreciate that the light above you, the device in your hand, the world you move through, all of it depends on something discovered piece by piece, understood gradually, applied patiently by people who came before, who asked questions and sought answers and shared what they learned. As this story draws to a close, as the words slow and the thoughts settle, I'm left with a simple appreciation for the invisible forces that shape our world, for the human capacity to understand them, for the long, slow accumulation of knowledge that brought us from darkness to light, from isolation to connection, from mystery to not certainty exactly, but understanding, workable understanding, sufficient to build a world, sufficient to power civilization, sufficient to illuminate the night. The electrons keep flowing through wires and circuits and devices, doing their work, moving in response to voltage, following paths laid down by engineers, carrying power and information and possibility. They've been flowing since the first generators spun, since the first batteries discharged, and they'll keep flowing, invisible and essential. The current beneath everything, the force we learn to harness, the light we learn to summon, the connection we learn to maintain. And perhaps that's where the story rests. Not ending, but simply pausing, acknowledging that electricity is not a conclusion but a continuation, not a destination but a journey still underway, still revealing new facets, still supporting new dreams, still humming quietly in the background, powering the world, lighting the darkness, connecting the scattered, making possible everything we've built, everything we've become, everything we might yet be. The lights glow softly, the current flows steadily, and the night, once so dark, is filled with illumination, with connection, with the gentle hum of civilization powered by understanding, by curiosity, by the long, slow, patient work of discovering us. And in that soft glow, in that steady hum, the story continues quiet and constant, invisible but everywhere, as fundamental as breath, as present as light, as essential as the current that flows endlessly through everything,